Good day, my name is JEEVAN CHETTIAR and today I'll be presenting the project of my group which is Group 5 from Section 3. Our project is titled as Finite Animal Analysis of a Rectangular Two-Tier Work Table Subjected to Static Loading Conditions. This study compares traditional analytic calculation with finite element analysis using LISA software to evaluate the structural behavior, stress distribution, and deformation of a two-tier work table under static loading conditions. Moving on, this slide represents the geometry and material properties of the selected work table. The structure has a length of 750 millimeters and a width of 300 millimeters and a height of 300 millimeters. The frame is constructed by using a 25 by 25 millimeter rectangular hollow section mild steel members with a wall thickness of 1 millimeter. For the analysis, standard mild steel properties were used, which includes a Young modulus of 200 gigapascals, Poisson ratio of zero point 0.3, density of 7,850 kilograms per cubic meter, and a yield strength of 250 megapascals. That will be all from me. Thank you.
Hi, my name is Yong and now I present this slide. This slide shows how the actual loading condition was converted into an engineering model. A concentrated load of 10 kilograms was converted into 98.1 newtons, while a distributed load of 30 kilograms was represented as a uniformly distributed load of 784.8 newtons per meter. By using the static equilibrium equations, the support reactions were calculated as 147.15 newtons at support A and 245.25 newtons at support B. For the analytical calculations, the actual 3D worktable was simplified into a 2D simply supported beam with a span length of 0.75 meters. This simplification allows classical equilibrium equations to be applied directly. Although this assumption ignores load redistribution through the frame and legs, it provides a conservative estimate by predicting the highest possible bending stresses. By using the calculated support reactions, the shear force diagram and the bending moment diagram were developed. The shear force crosses zero at a distance of 0.4 meters from the left support. Since the maximum bending moment occurs where the shear force becomes zero, the maximum bending moment was calculated as 38.32 Newton meters. Based on the analytical calculations, the maximum bending stress was found to be 14.69 megapascals. The maximum downward deflections were 0.482 millimeters. Using the yield strength of the factor of the safety was calculated as 17.02. These results indicate that the structure is capable of safely supporting the applied loads and remains well below the material's failure limit.
Thank you, Yong. My name is SYAFIQ. So while the analytical calculation provide a useful baseline, they simplify the structure into a single beam. Therefore, a three-dimensional finite element model was developed in LISA software to capture the actual frame behavior and load distribution within the structure. So this slide shows the finite element model developed in LISA software. The geometry was created using the measured dimension of the actual table. Material properties, loading condition, and support constraint were assigned to replicate the physical structure as close as possible. After creating the geometry, the structure was distributed into smaller finite elements through meshing. The mesh allowed the software to calculate stresses and displacement through the structure. A suitable mesh density was selected to achieve reliable result while maintaining computational efficiency. This slide presents the stress distribution obtained from the finite element analysis. The highest stress are concentrated near the frame, connection, and joint where the load are transformed between members. This location experiences great stress due to the interaction between horizontal and vertical frame elements.
This slide shows the deformation behavior of the structure under loading. The largest displacement occurs near the central region of the loaded members, which is consistent with the beam bending theory. However, the overall deformation remains relatively small, indicating adequate structural stiffness. This slide compares the analytical calculations with the finite element results. Although some differences exist due to the modeling assumptions, both methods show the similar structural behavior and confirm that the work table remains safe under the applied loading conditions. The comparison also validates the accuracy and the reliability of the finite element model. The key finding of this study is that the three-dimensional frame redistributes loads through the multiple members, reducing the localized stress concentrations compared to the simplified analytical model. This demonstrates that the advantage of the finite element analysis in representing real structural behavior more accurately.
Hi, my name is FIRHAN bin FAZLI. Today I want to present about conclusion. So in conclusion, both analytical calculation and finite element analysis were successfully used to evaluate the structural performance of the rectangular two-tier workable. The calculated stress and deflation values were well within acceptable limits, while the factor of safety exceeds 17. Therefore, the structure possesses adequate strength, stiffness, and stability under specified loading conditions. So for the recommendation, for future work, experimental testing is recommended to validate the analytical and finite element results. Additional loading scenario and more detailed modeling can also be considered to improve the accuracy of the analysis. With that, we would like to thank our lecturer, Prof. Madya, TS Dr. Muhammad Hafiz bin Zainul Abidin, and University Nusa on Malaysia for their guidance and support. Thank you for your attention.